Well, good morning. In the last class, we talked in terms of the contour nozzle. The shape of the contour nozzle is in the form of a bell. Initially, you expand the flow larger, you compress the flow later on, such that you get a very small value of divergence angle, let us say between 2 to 5 degrees. Initially, you expand the flow at a larger angle, say between 20 to 50 degrees. And the shape of this contour is something like a parabola. You fit in something like a second order parabola such that you can get this point and this point into this particular parabola. This is how a contour nozzle looks like. In today's class, let us look at some unconventional nozzles. And say, are there any better ways of having nozzles other than, let us say, conical nozzle, contour nozzle, and also maybe make our mindset little more clear what should be the future work which we must do on nozzles. I think that maybe another 10 minutes and then I will work out some examples. First I can tell myself, well, a nozzle operates at its optimum at a given value of ambient pressure. In other words, if I want to make a nozzle, I design it for, let us say, 15 kilometers, start operating it from 0 kilometers, and the rocket goes up to 30 kilometers. Initially 0 to 15 it is not optimum, at 15 it is optimum, beyond 15 again it is under expanded and not optimum. Therefore, can I have something like, let us say, a nozzle which I can have something like an extendable nozzle. Let me give you an example. Suppose I have a nozzle something like this, and this nozzle is operating at lower altitudes or higher pressures, and now I store, maybe I have to expand it out somewhere, again make it higher. Therefore, I initially store something like this, I bring it over here, I lock something over here. This initial nozzle operates at low altitude. The moment the nozzle goes to higher altitude, through some mechanism I shift this over here, I then maybe make it little go up still higher. That means this becomes my initial low area ratio nozzle. Corresponding to this, I have a higher area ratio nozzle. That means I extend the nozzle during the flight. During the lower altitude, I use a smaller area ratio nozzle, and then I store this on top of this, and when it reaches a particular altitude, I push it over here. The nozzle length increases, the area ratio increases, and this is what we call as an extendable nozzle. This was tried in a flight, but it is not used extensively, is not used at all, though it has been tried. We call it as extendable nozzle. If instead of having an extendable nozzle, the other alternative is, why not have a double bell nozzle or something like a dual bell nozzle. In other words, I have a nozzle like this, I want to increase the area ratio still further. What I do is I put something like a step over here, and then I continue this nozzle profile like this. Now this is my center line. Now what is going to happen at lower altitude? The flow expands to the ambient pressure, flow separates and flows over here. At higher altitude, because the pressure here is very much higher than the ambient pressure, the flow reattaches here. Therefore, I can get area ratio epsilon 1, area ratio epsilon 2 over here. This is known as a dual bell nozzle. In fact, this month's issue of AAA journal has a paper on this dual bell nozzle looking at the optimum conditions. That is, there is still work going on in this. Therefore, second we say is unconventional, first extendable nozzle, 2 is a dual bell nozzle. Third we say is radial nozzle, radial flow nozzle. What do I mean? Something like an something like what I say is an expansion deflection nozzle. Let me put one throat over here, let me say this is my convergent, I have a divergent like this is my center line over here, I put a throat over here, I put a block over here, something like a plug over here, I allow the flow to take place, and what happens? The flow is guided by the contour valve over here. At the center it is not guided, therefore I have something like an expansion wave, it is able to adapt to different altitudes, therefore by putting this I can make this particular nozzle operate at different altitudes. In other words, I have the outer wall which guides the flow, inner part is free, it can adapt to different altitudes, and therefore this is known as an expanded ED nozzle, expanded deflection nozzle. See, what we have to do is we want the nozzle to operate at different altitudes. Therefore, what we have done is we have done with a plug, we allow the contour to change the pressure of the outer flow, but inner flow we keep free such that the inner flow can expand and do this expansion deflection nozzle. As an extension of this, we could also have a nozzle, instead of having a plug here and allowing the outer thing to flow across a nozzle, I can have a nozzle, I can have this plug in the form of, let us say, a contour over here, center contour like this, and what I do is I bring the flow over here from the chamber. In other words, I have an annular chamber over here, I allow the flow to come across this, I allow the inner contour instead of the outer contour to balance the flow, keep the outer open such that it is again a case of an adapted nozzle, it can adapt to any condition. I could have it in the form of a spike, in which case I call it as a spike nozzle, or simply I call it as a plug, because I put this plug in this, I call it as a plug nozzle. I could still have some variation, this particular plug which is at the center, I could terminate it a little earlier, somewhere here, I do not allow the total spike. In other words, I have primary flow along this, I have the shock waves here and the secondary flow here, I have recirculation of base pressure here, and this becomes what we call as the aerospike nozzle. Let me make these things very clear. What we are saying, the combustion is happening over here, an annular combustion chamber, or I have the combustion chamber over here, somewhere over here combustion is taking place, I push the flow along this, I allow the spike to regulate it, instead of having an outer boundary which regulates the pressure, I have an inner boundary which corresponds to a spike, which we call as a plug nozzle or a spike nozzle, because this is a plug, and the same plug which we used in the case of a contour nozzle allowed the contour to deflect the flow, and here it was free, such that these are something which we can call as nozzle which can adapt to the ambient pressure. Aerospike, again we are having additional thrust coming from this, which we call as aerospike. But why should we always think in terms of a cylinder, a bell or something like that? Why not open out the bell, make it something like linear? If I have not a cylinder but I stretch out, I call it as linear nozzle. What do you mean by linear nozzle? Well, I open out the bell something like this, I have this as a contour, and now I allow the flow, this is a ramp as it were, I allow the gases to come along this, and it is guided by this particular ramp. In other words, I have something like this, let us say over here it could be shaped something like this, flow comes along this, guides along this and comes out, and similarly flow comes along this, this becomes something like a shape which is linear, or this could be one part of an aeroplane, like let us say a wing or a fuselage, and I allow the gas to come along it and flow along this, and these are certain known as linear nozzles. This has been used in the aircraft industry for the space plane. Let me not dwell on these things because these follow the same principle what we have discussed so far. I will not get into details, but I will just summarize it through a series of maybe slides over here. In the first slide here, I show the divergence losses, maybe alpha, and how we got the divergence loss coefficient. This was the value of delta, which we decided as percentage loss in thrust versus the angle alpha. We derived this. We told ourselves the nozzle is around 15 degrees or so for a conical nozzle. We talked in terms of a contour nozzle. We told ourselves instead of having a cone, I initially expand the flow to alpha I is between 20 to 15 degrees, and then bring it back. I have a low angle over here of the at the exit of something like 2 to 5 degrees or so. Smaller the angle at the exit, smaller is my loss what I have. This is the extendable segment. Initially I have a small area ratio corresponding to AE1. I store this on top of this. When I want to fly at higher altitude, I push it out, I get a larger value of this over here. This is a dual bell nozzle. As you see, this is the contour. I give a step over here, you see the step over here, and this is adaptable to different altitudes. And as I told you, there was a paper this month in AAA which deals with these bell nozzles. Those who are interested should go through it. This is a plug nozzle. I put a plug here. I have an outer surface which guides the flow. The inner surface is free, therefore it can adapt to the flow where it were. What you have is an annular throat instead of having a diametrical throat over here. This is what we say is a plug nozzle or a spike nozzle. I have a spike over here. The flow comes. The flow in these cases, you generate it in an annular chamber instead of having a chamber over here. I push the flow on to this inner surface, and inner surface guides the flow, outer surface is free, therefore I can have any type of expansion what I want. It is still not used in practice, and this summarizes what we learnt about nozzles. It is a conical nozzle. The nozzle runs hot, therefore to protect the nozzle I give insulation on the inner surface. This is the conical nozzle. I give something like a carbon which can take a lot of heat. I give some something known as ablative materials. I will come back to it when I deal with cooling of rockets. I will get back to this slide little later in the course, but this is how a practical nozzle looks like. This is the outer surface, this is the inner wall of this. I repeat this, a nozzle firing for a certain amount of time. This is a conical nozzle. You see that the nozzle runs red hot and you have the flow taking place, and this is where we said I have the waves and all that, and we talked in terms of shock diamonds. Well, with that we close the portion on nozzles, but it will be incomplete without doing one or two problems. In the next matter of 20-25 minutes I will do one of the problems, and the problem which I do is related to this particular vehicle. This vehicle is known as Saturn V vehicle. Let us put it down. Let us do this problem. See, Saturn V vehicle was used to put the first man on the moon. Therefore, you have Saturn V launch vehicle which puts the Apollo capsule carrying 3 men onto the moon. This is by far the biggest rocket ever made in the history of rockets, most powerful rocket. And what does it consist of? If you go back and look at this particular slide, the first stage of the rocket somewhere over here consists of 5 rockets clustered together. That means each one of these rockets is known as F1 rockets. It consists of 5 F rockets clustered together. The second, it uses kerosene and oxygen as fuel, kerosene as fuel and liquid oxygen as oxidizer. The second stage consists of 5 engines again, it is known as J2 engines. I will get back into the details of this. 5 J2 engines clustered together. This uses liquid hydrogen and liquid oxygen. The third stage consists of one single J2 engine. Therefore, what is it we are talking of? The Saturn V rocket consists of the first stage which consists of maybe 5 1 2 3 4 5 and these are 5 F1 engines or 5 F1 rockets together. The second stage similarly consists of a cluster of 5 J2 rockets. These are all name of the rocket, and J2 rocket uses liquid oxygen and liquid hydrogen as fuel. This uses kerosene and liquid oxygen as fuel, and on the third stage you have a single J2 rocket, and on top of this sits your particular capsule, which is the Apollo capsule, is where the 3 people who travel to the moon sit over here. And we would like to do an example. Let us take an example of F1 rocket. Before that, let us put some numbers down. J2 rocket has a thrust of something like 1000 Newton, 1100 Newton. Each of the J2 rockets here, mind you, the same J2 rockets when used for the second stage has a thrust of 1000, I am sorry, kilonewton, and each of the F1 rockets has a thrust of something like 3800 kilonewton. Let me make sure about the numbers. Yeah, this has something like, when I look at the force, please be very clear, this has a thrust of something like 110 ton thrust, because kilonewton, therefore we are talking of 10 Newton is equal to 1 kilogram, therefore we are talking of a huge force here. Therefore, why is it that the same engine when used in the second stage produces less thrust than when used in the third stage? Altitude, that means higher the altitude I get more specific impulse and therefore higher thrust. Therefore, let's take the example of one F1 rocket out of all these 5. Let us do the nozzle problem related to, let us say, one F1 rocket. The problem I consider is the thrust of this rocket is equal to 3800, is that what? No, my numbers are not correct. This gives me a much higher value, 6800, I am sorry. Yeah, this is 1000, this is 1100, this each one has a thrust of 6800. Kilonewton. The mass flow rate through the nozzle is equal to 2600 kilogram per second. These are typical numbers, we should keep in mind, we are not talking of 1 kilogram per second, we are talking of something like almost 3 tons of propellants going through the nozzle. The area of the nozzle is equal to 0.65 meter square. That means if I put it in terms of diameters, well, a man can easily stand at the throat or go through the throat of this nozzle. The molecular mass of gases which are passing through the nozzle is equal to 22 grams per mole. The temperature of the combustion products in the chamber is equal to 3300 Kelvin, and the chamber pressure is equal to 6.65 MPa, that means something like 66 bar. This is a little below the standard pressure of 7 MPa which we are talking of. Mind you, this rocket was developed in the period 1962 and we had the moon mission by 69. Therefore, we are talking of an old rocket, but mind you, it is still the most powerful rocket ever developed in the history of rockets, and that is why I thought maybe we should do a problem on this. Now, I want to find out for this F1 rocket the value of eta C star, the value of ISP, and the value of thrust correction factor zeta f. Let us do it. You know, because the nozzle is there, the area is there, you know the how much propellant is burnt per second. I just want to do this problem. Therefore, to be able to get the value of eta c star, I must get the value of c star which is actual. I must also get the value of c star which is ideal, right. The ratio of this is the c star efficiency. How do I get the ideal value? Well, we already know it is equal to under root r Tc by capital gamma, and the value of capital gamma, let us again substitute, r is equal to r naught divided by the molecular mass divided by Tc, and capital gamma is equal to under root gamma 2 over gamma plus 1 into gamma plus 1 divided by 2 into gamma minus 1. It is also told to you for a molecular mass of 22 gram per mole, the value of gamma for the gases is equal to 1.22. Therefore, I substitute the value of gamma is equal to 1.22 and the value of capital gamma works out to be equal to (0.652) under root 2 by 1.22 plus 1, 2.22 divided by 2 into 0.2 over here. And therefore, I want the C star ideal. For C star ideal is equal to, now let us substitute the value, R naught universal gas constant 8.314 joule per mole Kelvin. I think please write the units whenever we do a problem. The value of Tc for this particular propellant combination or whatever is used is 3300. The value of the molecular mass is equal to 22 grams per mole, but I am talking in terms of joule which is related to kilogram, therefore I say 0.022 kilogram per mole. This is important. Many of us, mainly I find students just putting 22 here, which is not right, because when I say mole I want the value of R in joule per kilogram Kelvin, and therefore it must be kilogram per mole, and the value of capital gamma we already said is equal to 0.652. And this must be in that numerator must be in this one, and the value of C star ideal becomes 1713. This is how we calculate the ideal velocity, right, ideal C star. That means the capacity, let us repeat this to ourselves, the capacity of kerosene and liquid oxygen to generate chamber pressure is given by C star ideal, and this capacity is 1713 meters per second. Now I want to get the value of C star, I have to calculate the actual value. How would I do it? I go back, look at the problem, the mass flow rate is given to me. The mass flow rate is given to me as 2600 is equal to 1 over C star into pressure. Pressure is given as PC 6.65 into 10 to the power 6 Pascal. AT is given as 0.65, and therefore the value of C star actual I calculate from this, which is 2600 kilogram per second. Yes, this C star will come out to be equal to this divided by 2600, and that will give me a value of 6.65 into 10 to the power 6 into 0.65 divided by 2600 is equal to 1663 meters per second, or rather the value of C star efficiency is therefore equal to the actual value 1663 divided by 1713, which is equal to 0.97. In fact, you find that the C star efficiency is quite high even for a rocket made in the year 1962. The present rockets like the Space Shuttle main engine has a efficiency of C star of the order of 0.99. This is the way we are. There is hardly any room for improving the combustion any further, and we have to understand, when we do liquid propellant rockets, we will try to understand how come we get such high values and what are the factors which govern it. Maybe we should use some of these tactics in the other propulsive devices also. Therefore, we have done one part of it, namely what is the C star of this particular F1 engine, right. The next one I would like to understand, I want to find out is what is the value of ISP. How do I do it? What is the specific impulse of this engine? Yes. I know the thrust is 6800 kilonewton. I know the mass flow rate is 2600. Well, it is simple, is not it? F specific impulse is equal to I over mp, which is equal to I over t divided by mp dot, impulse specific ISP, which is equal to force divided by m dot p, and which is equal to the value what you have, namely 6800 into 1000 Newton divided by 2600, and the value of specific impulse will come out to be equal to what, 2710. No, I think I should have it somewhere. Well, whatever this number gives me, I think it is less than 2710. You just get this value, this is the value of ISP, right. Now I want to get the value of the thrust correction coefficient zeta f. For this I need to do little more calculations. Let me erase this part of the board. I get zeta f is equal to, I have to somehow relate the forces ideal to the actual, right. How do I get the ideal value? This particular rocket, we tell ourselves it develops a thrust of 6800 kilonewton when the exit pressure is also sea level, or rather when the value of Pe of this rocket is equal to Pa, which is equal to 0.1 MPa, because it is tested, the test has been done at sea level, for which the exit pressure is equal to Pa. We are assuming here that the nozzle exit pressure is equal to the ambient pressure. Therefore, for this condition the value of F ideal is equal to m dot into Vj, because there is no pressure thrust coming, Pe minus Pa is 0, because Pe is equal to Pa. And how do I get the value of Vj? We know, we derived the expression Vj squared is equal to 2 of the enthalpy difference, which came out to be equal to 2 gamma by gamma minus 1 R naught molecular weight Tc into 1 minus Pe by Pc to the power gamma minus 1 by gamma, where Pe is equal to the ambient sea level pressure. Put in the numbers, R naught same thing, R naught is 8.314, m is equal to 0.022, temperature is given 3300, gamma is given 1.22, Pe is equal to 0.1 MPa, Pc is equal to the value what is given here 6.65 MPa, and you substitute it and you get the Vj as equal to 2710 meter per second. and therefore what is the value of thrust? Thrust is equal to m dot 2600 kilogram per second multiplied by this, and therefore the value of F ideal is equal to multiply it m dot Vj, which gives you the 2600, let us write it down, into 2710, which is equal to 70 46 into 10 to the power 3 Newton. What is the actual value of thrust? 6800 kilonewton. But how do I get the value of zeta f therefore? Therefore, my immediate reaction or anybody's immediate reaction would be to tell the value of zeta f, that is the thrust correction factor, is equal to F actual divided by F ideal. F actual is equal to, you get the value as 6800 is the actual value. The ideal value is somewhat larger, 7046 kilonewton, and therefore you will tell me that this value is equal to 0.965, and this is what one expects. But actually, this is an actual rocket in which we must also consider the effect of C star efficiency, we must also consider the effect of the thrust correction factor. In other words, ISP or the actual thrust goes as eta C star into the thrust correction factor into the value of ISP, which could be ideal. Therefore, if I were to correct for the C star effect, I should have zeta f is equal to 0.965 divided by the value of C star efficiency, which I got as 0.97, rather this works out to be 0.995, because this is only for the nozzle. Because I looked at the total problem and the total problem gave me this, I have to isolate what is the contribution of the nozzle, and therefore the contribution of the nozzle is 0.995, whereas the contribution from the combustion or from the value of pressurization or C star is only 0.97 over here. I think this is how we get the efficiencies. Well, I would be happy even if we put a number 0.965, but let us keep in mind 965 also includes the value of C star efficiency, and that is why I had to remove it, and that is where I got this particular number. Let us take one more problem, a problem of rocket flying at different altitudes. Let me pose this problem to you first. Yes, let us say a booster rocket. Flies between sea level 0 kilometers to 30 kilometer altitude. The chamber pressure of this rocket PC is given to be 7 MPa, that is 70 bar. The value of the combustion product specific heat ratio is 1.2, and the throat area AT is equal to 0.1 meter square. Since this rocket flies between 0 to 30 kilometer altitude, the designers felt, let the nozzle be designed for mean of the two, say 15 kilometer altitude. Now, I want the following: determine the nozzle expansion ratio epsilon, the value of AE, second the value of CF, thrust coefficient at 30 kilometer altitude, and what is the optimum at 30 kilometer altitude. And 3, I also want to know till what height, till what altitude will flow separation occur. In other words, we assume it is a conical nozzle, flies between 0 to 30 kilometers. The nozzle is designed for an altitude of 15 kilometers. I want to know till what height flow separation takes place in this conical nozzle. I also want to find out the area ratio, the area at the exit, the thrust coefficient at 30 kilometer, optimum value of thrust coefficient at 30 kilometers, and to what altitude will flow separation takes place. Let us do this problem. We need some data, and the data which we normally use is something known as ICAO tables. You know, we need to know height in altitude versus the ambient pressure. This is given in the form of ICAO. It is known as International Civil Aviation Organization. These give some standards, and they will tell you, well, if the altitude versus the pressure, ambient pressure in Newton per meter square, if as at sea level the pressure in Newton per meter square is 101325 Newton per meter square, if the altitude is 4 meters high, the value is 61660. If the altitude is 8 kilometers, the value is 36651. You see the value keeps decreasing. Let us put 2 or 3 more. 12 kilometers, the value is 19399. If the altitude is 16 kilometers, it is 10353. If it is 20 kilometers, it is 10353. You know, if it is 20, it is 5529, and if it is 30 kilometers, the value of pressure is equal to 1186. Since I do not give the value at 15, let us assume that the nozzle is designed for 16 kilometer altitude, so that the ambient pressure table is available to us. For now, let us try to do these 3. We would like to first calculate the area ratio of the nozzle and the exit area. What do we tell? We say, well, the nozzle is designed for 16 kilometer altitude, therefore for 16 kilometer altitude we will have PE is equal to PA, and therefore what should be the value of PE for the nozzle? $10,353. Because the nozzle is designed for this particular altitude. That means when here 10,353. Other data is given. What is the value of PC? Is equal to, I go back, it is 7 MPa. We say 7 into 10 to the power 6 Newton per meter square. Gamma is given to you 1.2. Therefore, you immediately write out the expression for the area ratio. What was the expression? Let us go back to your notes. Epsilon is equal to 2 over gamma plus 1. You all can easily derive it out. It is not anything difficult. I do not want us to memorize anything. PC by PE 1 over gamma divided by under root gamma plus 1, gamma minus 1, 1 minus you substitute the values, you get the value as equal to 52.5. Area ratio of the nozzle is therefore 52.5. The value of the exit area AE by AT is equal to 52.5, or rather AT is given to you as 0.1 meter square, therefore the value of AE 5.25 meter square. Is it all right? Simple, we just, and this is how rockets tend to be extremely simple. And in fact I keep joking all the time, when we start doing something, in India we still have not made a good diesel engine or internal combustion engine or gas turbine engine. We have been taking time to do it and we are still not able to do, whereas rockets are very easy to do, and that is why we see spectacular progress in making of rockets. It is quite simple. Therefore you have AE is equal to 5.25 meter square. Therefore let us go to the next part of the program. CF at 30 kilometers, how do I evaluate it? What will be involved in this? We had derived the expression for CF, let us go back and take a look at it. CF is equal to 2 gamma square divided by gamma minus 1, 2 over gamma plus 1 divided by gamma plus 1 divided by gamma minus 1 into 1 minus P by Pc to the power gamma minus 1 by gamma, which is all under root, plus P by Pc. You will recall we did this in the morning, Pa by Pc epsilon. Please check. Now what are the values? I am interested at thrust coefficient at 30 kilometers. What are the values I put? You all must tell me. Well, you told we know gamma is equal to 1.2, that is given. What is the value of Pe? What is the value of Pc? And what is the value of Pa? Epsilon we have already determined as equal to 52.5. What is the value of P? Which value? Yes. Yes.
10,353.
Yes, the nozzle has been designed for 16 kilometer altitude, and that is where the exit pressure should be, and because it is now flying at a higher altitude but exit pressure will not change, therefore Pe is equal to 10,353. Your answer is correct. Pc we know is 7 into 10 to the power 6 Newton per meter square. Pa at the current altitude of 30 kilometers 1186. You substitute it and you get the value of Cf as equal to, I use the other side of the board, .828 plus 0.0687, which is equal to 1.896. Please check these numbers. Now what is the optimum value at 30 kilometers? Let me go back. In this expression itself you can tell me gamma is still the same. What will be the optimum value at 30 kilometer altitude? Well, Pe is equal to Pc, therefore optimum, therefore this term will get knocked out. And what will be the value of Pe if it is optimum? Yes, let us take a look at this table. Optimum at 30 kilometer, that means I will have a nozzle which gives me this value 1186, therefore I now change the value of Pe equal to 1186, this gets knocked out, and the value of Cf which now becomes Cf dot, will now become something like 2.246. You see, thrust coefficient is in the ballpark number of around 2 to 3, that number. Therefore, what is the percentage reduction from optimum? That means what has happened? You had a nozzle, I think I'll erase this out now. You had a nozzle which was designed for 16 kilometers, you are operating it at 30 kilometers. If it was designed for 30 kilometers, it would have been optimum at 30 kilometers. I have the value of Cf dot is equal to what I get, 2.246, but since it is designed for a lower value of area ratio and I get a lower value of the pressure recovery as 0.0687 and I do not get this number to be high, I get the total number as equal to 1.896, and therefore I can tell that the percentage reduction from optimum is equal to 2.246 minus 1.896 divided by 2.246. In other words, I have something like 0.156 or something like 15.6% reduction from the optimum. Therefore, you see the importance. If I have something like, I am not able to get the nozzle to expand, in fact I am having an under expanded nozzle, and that is why I am losing something like 15.6%. Had my nozzle been designed for 30 kilometer height, I would have got, but then I would have got a problem of over expansion or flow separation. Can we therefore go to the next part of the problem and determine the altitude till which the nozzle is over expanded or the altitude till which the flow separation takes place? We want to determine the altitude till which the nozzle is over expanded. For this, we apply the Summerfield criterion, which states that when the exit pressure of the nozzle is less than or equal to 0.4 times the ambient pressure, then the flow is over expanded, and this we looked at it. We also looked at a better criterion, namely involving Mach number also. Let us use the Summerfield criterion. If we say this, when the ambient pressure Pa is greater than or equal to Pe divided by 0.4, then we can say when the ambient pressure is greater than or equal to the exit pressure divided by 0.4, then the nozzle is over expanded. Therefore, let us do this problem now. Let us examine the changes in the ambient pressure with respect to altitude. Let me plot the table again for the specific altitudes of interest. Let us make a table of altitude in kilometer and the ambient pressure Pa at this particular altitude in Pascal. Let's plot it for something like 2 or 3 altitudes for which we are interested. At the altitude of 8 kilometers, the ambient pressure is 36,651 Pascal. At the altitude of 12 kilometers, the value of the ambient pressure is now 19, it has reduced because the altitude has gone up to 399 Pascal. At 16 kilometers, for which this particular nozzle is designed, the ambient pressure is 10,353 Pascal. the question is the nozzle is designed for 16 kilometers, therefore, the exit pressure of the nozzle is 10,353 Pascal. We want to find out the condition at which maybe as the rocket goes up, the altitude at which the flow begins to separate or the nozzle gets to be over expanded nozzle. Therefore, we have to state here that flow separation we have just written PA must be greater than or equal to PE divided by 0.4, and PE anyway the nozzle is defined or designed for an ambient pressure of or for a pressure of 10,353 Pascal. Therefore, PA must be greater than or equal to 10,353 divided by 0.4, and this is equal to 0.259 into 10 to the power 5 Pascal. Now, the question is when the ambient pressure is equal to or just greater than this value, the flow separation starts, or when the pressure is greater than this value, the flow separation starts, and what is the corresponding altitude? Now, when PA is equal to 259, it is somewhere between 8 and 12 kilometers. Therefore, we say at 8 kilometers the ambient pressure is 36,651 minus the value at 16 kilometers is 10,353, but we are interested in the altitude at 0.259 into 10 to the power 5. Therefore, we have the value of now 2, 5, then 900 minus the value at 16 kilometers 10,353, and this change in kilometer from 36 to 10 corresponded to a value of something like 8 kilometers. Therefore, this is 8, and therefore, we have 8 kilometers plus the change is 25 to 10,353, and therefore, the value is 8 plus this so much kilometers, and this works out to be something like 8 plus 2.16, which is equal to 10.16 kilometers. Therefore, this is the altitude at which flow separation stops, or thereafter the nozzle is either runs full or is under expanded. This is all about nozzles. In the next class we will start with chemical propellants. We will again keep it very simple, in the sense we will look at what are the requirements of chemical propellants and then see what are the propellants we must use, and I think that is what we will do next. Well, thank you then.